At the center of a black hole, the laws of physics as we understand them cease to apply. Not in the sense that they become difficult to apply, or that we lack the computational power to follow them, but in the deepest possible sense, the equations that describe the behavior of space, time, matter, and energy produce results that are mathematically undefined. Infinities that cannot be interpreted as physical quantities. We have a word for this breakdown: singularity. And the singularity at the center of a black hole is the universe keeping a secret, behind a door that once you cross it, you can never come back through. Tonight, we go to the door. We will not cross it, but we will stand at its edge in the dark and examine everything we know about what lies beyond it and what the universe does with the information of everything that falls through. Breathe slowly. The room you are in is dark and quiet, and the nearest black hole to Earth is about 1,000 light years away, a stellar mass black hole called Gaia BH1, discovered in 2022 in the constellation Ophiuchus. It is not doing anything dramatic tonight. It has no nearby companion star to accrete material from. It is simply sitting in the dark, 1,000 light years away, curving space-time around itself in silence. There are almost certainly closer black holes that we have not yet found, because black holes that are not actively accreting are nearly impossible to detect. The galaxy may contain 100 million stellar mass black holes, one for every massive star that has ever died. You have never been aware of them. They have always been there. A black hole is a region of space-time in which the gravitational field is so strong that nothing, not matter, not radiation, not light itself, can escape. The boundary of this region is called the event horizon. Anything that crosses the event horizon is forever cut off from the rest of the universe, not merely trapped in the way a ball thrown upward is temporarily trapped before falling back, but permanently and absolutely separated, in the same sense that the past is separated from the present. You cannot go back. The event horizon is a surface in space-time, not in space. It is defined by causality, by the structure of light cones, not by any material barrier. There is nothing physically unusual at the event horizon. No wall, no membrane, no sign of any kind. If you fell through the event horizon of a sufficiently large black hole, you would not necessarily notice the moment of crossing. The space around you would look and feel the same. The light from distant stars would still reach you. You could still read a book, think a thought, feel your heartbeat. You would simply be in a region of space-time from which no future path, however you tried to alter your trajectory, leads back to the outside universe. The concept of a black hole emerges naturally from general relativity, Albert Einstein's theory of gravity, published in 1915. General relativity describes gravity not as a force, in Newton's sense, but as the curvature of space-time produced by the presence of mass and energy. Objects that appear to be falling under gravity are actually following the straightest possible paths, geodesics, through curved space-time, a month after Einstein published his field equations. The German physicist Karl Schwarzschild solved them exactly for the case of a non-rotating, uncharged spherical mass. Schwarzschild's solution contains a remarkable feature. At a specific radius from the center, the metric of spacetime becomes singular. This radius, now called the Schwarzschild radius, defines the event horizon of a non-rotating black hole. The Schwarzschild radius of a mass m is given by 2gm divided by c squared, where g is Newton's gravitational constant and c is the speed of light. For the Sun, with a mass of approximately 2 times 10 to the power of 30 kilograms, the Schwarzschild radius is about 3 kilometers. If all the mass of the Sun were compressed into a sphere 3 kilometers in radius, a sphere smaller than many cities on Earth, the gravitational field at the surface would be so strong that not even light could escape, and the Sun would become a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. A marble-sized Earth would be a black hole. For a human being of average mass, the Schwarzschild radius is about 10 to the power of minus 25 meters. Far smaller than a proton, you will not become a black hole. But the calculation is available to anyone. Schwarzschild himself sent his solution to Einstein from the Eastern Front of World War I, where he was serving as an artillery officer and had contracted a fatal illness that would kill him within months. He died in May 1916, 5 months after publishing his solution and never knowing what his equations would eventually mean. Einstein, when he received the solution, wrote to Schwarzschild that he had not expected so exact a solution to be found, and he spent years afterward insisting that real black holes could not form, that some process of stellar physics would always prevent matter from collapsing inside its Schwarzschild radius. He was wrong. Let your breathing slow. The formation of a stellar mass black hole begins with the death of a massive star, a star with a mass at least 20 to 25 times that of the Sun. During its main sequence life, such a star fuses hydrogen into helium in its core, then helium into carbon, and onward through the periodic table, carbon to neon, neon to oxygen, oxygen to silicon, and finally silicon to iron. Iron is the end of the road. Iron fusion does not release energy, it consumes it. When an iron core accumulates at the center of a massive star, reaching a critical mass of about 1.4 solar masses, the pressure of electron degeneracy, the quantum mechanical resistance of electrons to being confined, can no longer support the weight of the overlying stellar layers. The core collapses in less than a second, from a sphere the size of Earth to a sphere about 10 kilometers in radius. The density of the collapsed core exceeds the density of an atomic nucleus. Neutrons and protons are crushed together. The collapse is so rapid and the rebound so violent that the outer layers of the star are expelled in a supernova explosion, briefly outshining the entire galaxy containing it. What remains at the center depends on the mass of the collapsing core. If the core mass is between about 1.4 and 3 solar masses, a neutron star forms, an extraordinarily dense object in which all the matter is essentially nuclear matter. If the core exceeds about 3 solar masses, no force known to physics can halt the collapse. The matter falls inward through whatever densities nuclear physics and particle physics can describe, and continues. General relativity predicts that it reaches a singularity, a point of infinite density and zero volume, at the center of what is now a black hole. The singularity is not a place in space. It is an endpoint in time, a moment that all infalling matter must eventually reach, in the same sense that the future is not a place you can avoid, but a time you must eventually reach. There are 4 types of black holes recognized in astrophysics, though only 3 have been observationally confirmed. Stellar mass black holes formed from collapsing massive stars have masses between about 3 and 100 solar masses. They are the most numerous. Intermediate mass black holes, with masses between 100 and 100,000 solar masses, are more poorly understood and less well observed. Though several candidates have been identified in globular clusters and dwarf galaxies, supermassive black holes with masses between about 1 million and 1 billion solar masses or more reside at the centers of almost all large galaxies. The Milky Way's central black hole, Sagittarius A star, has a mass of about 4 million solar masses. M87 star, the first black hole ever imaged directly, has a mass of about 6.5 billion solar masses. The fourth class, primordial black holes, may have formed in the very early universe from density fluctuations before any stars existed. Their existence has not been confirmed, but they remain a candidate for some fraction of the universe's dark matter. The no-hair theorem is one of the most remarkable results in the theory of black holes. It states that a stationary black hole is completely characterized by only 3 quantities: its mass, its electric charge, and its angular momentum, its spin. Nothing else. All other information about the matter that formed the black hole or fell into it is gone from the accessible universe. The black hole has no hair, in the sense of having no additional distinguishing features. A black hole formed from the collapse of a spinning star of one chemical composition is, from the outside, physically indistinguishable from a black hole formed from the collapse of a non-spinning star of a different composition with the same total mass, charge, and angular momentum. The rich complexity of the infalling matter, its temperature, its structure, its information, is erased from the external universe. Where it goes, whether it is truly destroyed or merely hidden, is the information paradox, one of the deepest unsolved problems in theoretical physics. Most real black holes are rotating. When the massive star that forms a black hole is itself rotating, as most stars are, the angular momentum is conserved, and the resulting black hole spins. A rotating black hole is described not by the Schwarzschild metric, but by the Kerr metric, derived by the New Zealand physicist Roy Kerr in 1963. The Kerr metric contains several features absent in the Schwarzschild case. The event horizon is smaller for a given mass, because the rotation adds centrifugal support. There is an outer region called the ergosphere, a region outside the event horizon, but in which space-time itself is dragged around by the spinning black hole in a phenomenon called frame dragging. Objects in the ergosphere cannot remain stationary relative to distant observers. They are forced to co-rotate with the black hole. Dragged along by the rotating spacetime, the ergosphere allows for a process called the Penrose process, by which energy can be extracted from a rotating black hole by sending a particle into the ergosphere, splitting it, and allowing one fragment to fall through the event horizon, while the other escapes with more energy than the original particle had. Rotating black holes are therefore reservoirs of energy, and the extraction of this rotational energy is thought to power the relativistic jets seen emerging from active galactic nuclei. Let the thoughts in your mind slow, like objects falling toward a black hole, asymptotically, never quite arriving. At 1.5 Schwarzschild radii from the center, there is a surface called the photon sphere. where the gravity of the black hole is strong enough to bend light into circular orbits. A photon traveling exactly tangentially to the photon sphere would orbit the black hole indefinitely, in principle forever, though in practice any small perturbation would cause it to spiral in or spiral out. The photon sphere is unstable. Circular light orbits exist there but cannot be maintained. If you were hovering at the photon sphere and looked sideways, you would see the back of your own head, because light from behind you has been bent around the black hole to reach your eyes from the front. The photon sphere is what produces the dark shadow seen in Event Horizon Telescope images of black holes, ringed by a bright ring of photons on near circular orbits. Gravitational time dilation near a black hole is not science fiction. It is a direct consequence of general relativity, well tested in weaker gravitational fields and extrapolated into the strong field regime near black holes. Time runs more slowly in a stronger gravitational field. At a distance of about 1.01 Schwarzschild radii from the center, hovering just outside the event horizon, a clock would tick about 7 times more slowly than a clock at infinity. At the event horizon itself, from the perspective of a distant observer, a clock falling inward appears to slow to a stop and redshift to invisibility, frozen forever at the moment of crossing. From the perspective of the infalling clock, no such freezing occurs. The crossing happens in finite proper time. The clock continues to tick normally, and the horizon is crossed without drama. The film Interstellar, released in 2014, depicts a planet in the gravitational field of a supermassive black hole called Gargantua, where 1 hour of surface time corresponds to 7 years of distant time. The physics of this scenario was worked out by the physicist Kip Thorne, one of the founders of LIGO, who served as scientific consultant for the film. For the time dilation depicted to be accurate, the planet would need to be at a distance of about 1 + 1 × 10 to the power of -14 Schwarzschild radii from the event horizon of a maximally rotating Kerr black hole of about 100 million solar masses. The physics is real. The scenario, while requiring an implausible degree of precision and orbital placement, does not violate any known law of physics. Now consider spaghettification. The word was coined by Stephen Hawking, and it describes exactly what it sounds like: the process by which an object falling into a black hole is stretched lengthwise and compressed laterally by differential gravitational forces until it is drawn out into a long, thin strand of matter. The cause is the tidal force, the difference in gravitational acceleration between different parts of the infalling body. If you are falling feet first toward a black hole, your feet are closer to the center and therefore experience a stronger gravitational pull than your head. This differential pull stretches you in the direction of the fall. Simultaneously, you are compressed from the sides. Because gravity pulls all parts of your body toward the center, the parts of you to the left are pulled slightly to the right, and the parts to the right are pulled slightly to the left, compressing your lateral dimensions. For a stellar mass black hole of about 10 solar masses, spaghettification begins far outside the event horizon. The tidal force at the event horizon of such a black hole is approximately 10 to the power of 22 times the surface gravity of Earth, a force that would tear apart any known material structure long before anything reached the horizon. An astronaut falling toward a 10 solar mass black hole would be disintegrated by tidal forces at a distance of about 400 kilometers from the center, still far outside the event horizon at about 30 kilometers. Spaghettification for a stellar mass black hole is violent and unmissable. For a supermassive black hole, the situation is different. The tidal force at the event horizon scales as the inverse cube of the Schwarzschild radius, which scales as the mass. For a black hole of 4 million solar masses, like Sagittarius A star, the tidal force at the event horizon is about 10 to the power of 9 times weaker than for a 10 solar mass black hole. For a black hole of several billion solar masses, the tidal force at the event horizon would be weaker than the surface gravity of Earth. An astronaut falling into M87 star, a black hole 6.5 billion times more massive than the Sun, would cross the event horizon, which is located at a radius of about 19 billion kilometers, without feeling any particularly unusual tidal forces. They would have no physical sensation at the moment of crossing. The spaghettification would come later, as they fell toward the central singularity, where the tidal forces grow without bound. The singularity itself is not a place, but an edge of spacetime, a boundary beyond which the geometry of spacetime cannot be extended. General relativity predicts that once inside the event horizon, all future directed paths, all world lines of matter and light, lead to the singularity. Not because the singularity is pulling everything toward it, as if it were a massive object in the conventional sense, but because the singularity is in the future of everything inside the horizon. Time inside a black hole runs toward the singularity in the same way that time outside a black hole runs toward the future. You cannot avoid the future. You cannot avoid the singularity. The time between crossing the horizon and reaching the singularity of a 10 solar mass black hole, measured in proper time for a freely falling observer, is about 0.0002 seconds. For M87 star, it would be about 12 hours. Even after crossing the event horizon of the most massive black hole known, you would have half a day of proper time before the singularity. Outside the black hole, the story of what happens to the infalling matter continues in a different form. In the 1970s, Stephen Hawking combined general relativity with quantum field theory in the vicinity of a black hole's event horizon and derived a stunning result. Black holes are not perfectly black. They emit radiation. The mechanism involves the vacuum fluctuations of quantum field theory. In quantum mechanics, the vacuum is not truly empty, but is filled with pairs of virtual particles that appear and annihilate in times too short to violate the uncertainty principle. Near the event horizon of a black hole, one member of such a pair can fall through the horizon while the other escapes to infinity. The escaping particle carries positive energy and constitutes the Hawking radiation. The infalling particle carries negative energy relative to the external observer, reducing the mass of the black hole. Over astronomical timescales, a black hole radiates away its mass entirely, shrinking and growing hotter as it does, until in its final moments it evaporates in a burst of radiation. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes are hotter. The Hawking temperature of a black hole is given by h bar c cubed divided by 8 pi g mk sub b, where h bar is the reduced Planck constant, c is the speed of light, g is Newton's gravitational constant, m is the mass of the black hole, and k sub b is Boltzmann's constant. For a black hole of 1 solar mass, the Hawking temperature is approximately 60 nanokelvin, far colder than the 2.7 Kelvin of the cosmic microwave background radiation that fills the universe. Such a black hole would absorb far more radiation from the cosmic microwave background than it emits as Hawking radiation and would actually gain mass. Black holes of stellar mass are currently growing, not evaporating, and will continue to do so for as long as the cosmic microwave background temperature exceeds their Hawking temperature, which is on cosmological timescales of order 10 to the power of 19 years. For a black hole to evaporate in the current age of the universe, it would need to have a mass of about 5 times 10 to the power of 11 kilograms, roughly the mass of a mountain compressed into a volume much smaller than a proton. Such primordial black holes, if they formed in the early universe, would be evaporating today, their final moments appearing as bursts of gamma radiation. No confirmed detection of such an evaporation event has been made. For a stellar mass black hole of 10 solar masses, the evaporation timescale is approximately 2 times 10 to the power of 67 years, far longer than the current age of the universe, which is about 1.38 times 10 to the power of 10 years. For M87 star at 6.5 billion solar masses, the evaporation timescale is about 10 to the power of 83 to 10 to the power of 100 years. The universe, which is currently 13.8 billion years old, has barely begun relative to the timescale on which these black holes will evaporate. Black hole thermodynamics is one of the most beautiful structures in theoretical physics. Jacob Bekenstein showed in 1972 that black holes must possess entropy proportional to the area of their event horizons, and Hawking's subsequent derivation of black hole temperature completed the picture. There are 4 laws of black hole mechanics, in precise analogy with the 4 laws of thermodynamics. The zeroth law, the surface gravity of a stationary black hole, is constant over its event horizon, analogous to the zeroth law of thermodynamics, which states that the temperature of a system in thermal equilibrium is uniform. The first law, changes in the mass of a black hole, are related to changes in its area, angular momentum, and charge, an analogy with the conservation of energy in thermodynamics. The second law, the total area of event horizons can never decrease, analogous to the second law of thermodynamics, stating that entropy never decreases. The third law, the surface gravity of a black hole cannot be reduced to 0 by any finite sequence of operations, analogous to the third law of thermodynamics, stating that absolute 0 temperature cannot be reached. The second law of black hole mechanics, the area theorem, was proven by Hawking in 1971 using classical general relativity, but it was in tension with the second law of thermodynamics. If you throw a cup of hot tea into a black hole, the entropy of the tea disappears from the outside universe, apparently violating the second law. Bekenstein resolved this by arguing that the entropy of the black hole increases when matter falls in, and that the total generalized entropy, the sum of ordinary thermodynamic entropy outside the black hole and the entropy of the black hole's horizon, never decreases. But Hawking radiation introduces a complication Black holes do evaporate, their area does decrease, and their entropy does decrease. This is consistent with the generalized second law only if the Hawking radiation itself carries entropy, which it does, but the question of whether it carries the specific information content of everything that ever fell into the black hole is the information paradox. Let yourself settle completely into the quiet. Sagittarius A star, the supermassive black hole at the center of the Milky Way, is 26,000 light-years from Earth in the direction of the constellation Sagittarius. Its mass is approximately 4 million solar masses, corresponding to a Schwarzschild radius of about 12 million kilometers, or about 17 times the radius of the Sun. It is surrounded by a dense cluster of stars called the S-star cluster, within a few thousandths of a parsec of the black hole. These stars move at extraordinary velocities as they orbit the black hole. The star designated S2 has an orbital period of only 16 years and a periapsis distance of about 120 astronomical units from the black hole, at which point its orbital velocity reaches about 650 kilometers per second, about 2.5% of the speed of light. The orbits of the S-stars provided the first incontrovertible proof that Sagittarius A star is a massive compact object, most likely a black hole, in the 1990s and 2000s, work that earned the 2020 Nobel Prize in Physics for Andrea Ghez and Reinhard Genzel. The Event Horizon Telescope, a global network of radio observatories linked by the technique of very long baseline interferometry to create an effective aperture equal to the diameter of the Earth, produced the first direct image of a black hole's shadow in April 2019. The target was M87 star, the supermassive black hole at the center of the galaxy M87, 55 million light-years away. The image shows a bright ring of emission from hot plasma orbiting the black hole, with a dark central region, the shadow, where the black hole prevents light from escaping. The ring has a diameter of about 42 microarcseconds as seen from Earth, corresponding to a physical diameter of about 10 Schwarzschild radii for a black hole of 6.5 billion solar masses. In May 2022, the collaboration released the first image of Sagittarius A star itself, a more technically challenging result because the plasma near Skrar A star varies in brightness on timescales of minutes, requiring special time averaging techniques to produce a stable image. Both images confirmed the predictions of general relativity for the appearance of black holes with high precision. M87 star is also the source of one of the most spectacular phenomena in astrophysics, a relativistic jet. The jet is a stream of plasma launched along the rotation axis of the black hole, extending for about 5,000 light-years from the galactic center, and carrying material at velocities that appear superluminal in projection. Because the jet is moving nearly along the line of sight and nearly at the speed of light, the apparent sideways motion of jet features can exceed the speed of light as seen. From Earth, an effect called superluminal motion that does not violate special relativity, but is simply a geometrical effect. The mechanism by which relativistic jets are launched is not fully understood, but the leading model, the Blanford's-Najek process, involves the extraction of rotational energy from the spinning black hole through the magnetic field of the accretion disk. Converting the kinetic energy of the black hole's spin into the kinetic energy of the jet. Accretion disks form when matter falling toward a black hole has angular momentum and cannot fall directly to the center. The infalling material settles into a disk, spiraling gradually inward as angular momentum is transported outward through the disk by viscosity, turbulence, and magnetohydrodynamic instabilities. As material spirals inward, it loses gravitational potential energy, and this energy is converted to thermal energy, heating the disk. The temperature of the accretion disk increases toward the inner edge. For a stellar mass black hole, with a disk accreting at a significant fraction of the Eddington rate, the maximum temperature in the disk is about 10 to the power of 7 Kelvin, producing X-ray emission. For a supermassive black hole powering a quasar, the disk temperature can reach 10 to the power of 12 Kelvin in the innermost regions, producing the extraordinary luminosity that makes quasars visible across billions of light years of cosmic distance, outshining their host galaxies of hundreds of billions of stars. The binary black hole mergers detected by LIGO are among the most violent events in the universe since the Big Bang. When two stellar mass black holes in a binary system spiral toward each other, losing orbital energy to gravitational wave emission, they eventually merge in a fraction of a second. The merger of two black holes of 29 and 36 solar masses, which produced the first detected gravitational wave event, GW 150914, on September 14, 2015, released approximately 3 solar masses of energy as gravitational waves in about 0.2 seconds. The peak power of this emission was approximately 3.6 times 10 to the power of 49 watts, which exceeds the combined electromagnetic luminosity of all stars in the observable universe. The gravitational waves from this merger, having traveled 1.3 billion light years, compressed and stretched the 4-kilometer arms of the LIGO detectors by a distance of about 4 times 10 to the power of minus 18 meters, about 1,000 times smaller than a proton. This was the most precise length measurement in the history of science. The information paradox, first clearly articulated by Hawking in 1976, remains one of the deepest unsolved problems at the intersection of quantum mechanics and general relativity. If a black hole forms from matter in a specific quantum state and then evaporates via Hawking radiation, the radiation appears to be thermal, characterized entirely by the temperature, and therefore contains no information about the specific quantum state of the matter that formed the black hole. This would mean that a process involving a black hole is fundamentally non-unitary, destroying quantum information, which would violate the foundational principles of quantum mechanics. Most physicists believe that information cannot be truly destroyed and must be encoded somehow in the Hawking radiation, but the mechanism by which pure states map to pure states through the formation and evaporation of a black hole is not understood. In 2019, a group of physicists showed using the concept of quantum islands, regions of space-time that are quantum mechanically entangled with the Hawking radiation, even though they are inside the black hole horizon, that the entropy of the Hawking radiation follows the Page curve. The entropy first increases, then decreases as the black hole evaporates, exactly as required for a unitary process in which information is preserved. This result, obtained using techniques from the AD-SCF holographic correspondence, is broadly considered the strongest evidence yet that information is preserved in black hole evaporation, but the precise physical mechanism by which information escapes the black hole remains obscure. Tidal disruption events are among the most dramatic phenomena associated with supermassive black holes. When a star wanders too close to a supermassive black hole, the tidal force of the black hole can exceed the self-gravity of the star, pulling it apart in a violent disruption. Approximately half the stellar material is ejected on hyperbolic orbits and escapes the black hole's gravity. The other half falls into a highly eccentric orbit and gradually circularizes into an accretion disk, feeding the black hole at a rate that peaks above the Eddington limit before declining over months to years. The resulting flare of radiation, brightest in ultraviolet and soft X-ray wavelengths, can briefly outshine the entire host galaxy and is detectable from billions of light years away. Surveys by the Zwicky Transient Facility and other wide-field optical telescopes now detect dozens of tidal disruption events per year, providing a new window on the supermassive black holes lurking at the centers of otherwise quiet galaxies. The most massive black holes known are found at the centers of the most massive elliptical galaxies. Tone 618, a quasar at a redshift of 219, corresponding to a look-back time of about 10.4 billion years, contains a black hole with a mass of approximately 66 billion solar masses, making it the most massive black hole with a reliably measured mass. Its accretion disk is so luminous that it is one of the most intrinsically bright quasars known, with a bolometric luminosity of about 4 times 10 to the power of 40 watts, about 100 trillion times the luminosity of the Sun. Home 15A star, the central black hole of the galaxy Home 15A and the Abell 85 cluster, has a mass estimated at approximately 40 billion solar masses, making it the most massive black hole with a mass measured from stellar dynamics. Its Schwarzschild radius is approximately 120 billion kilometers, about 800 astronomical units, larger than some estimates of the Oort cloud's inner edge. The event horizon of Home 15A star is a sphere spanning a volume comparable to the inner solar system. The Eddington luminosity is the theoretical maximum luminosity that a black hole or any gravitational source can achieve through steady accretion, the luminosity at which radiation pressure on the infalling matter balances gravitational attraction. Above the Eddington limit, radiation pressure would blow away the infalling material, quenching the accretion. The Eddington luminosity scales with mass. For a black hole of 1 solar mass, it is about 1.3 times 10 to the power of 31 watts, about 30,000 times the luminosity of the Sun. For a black hole of Ton 618's mass at 66 billion solar masses, the Eddington luminosity is about 8 times 10 to the power of 41 watts. Ton 618 is accreting at close to its Eddington limit, which is consistent with its era. At a redshift of about 2, roughly 3 billion years after the Big Bang, the universe contained abundant cold gas for black holes to accrete, and quasars were far more common than they are today. The relationship between supermassive black holes and the galaxies they inhabit is one of the most striking discoveries of modern astrophysics. The mass of the central black hole of a galaxy correlates tightly with the velocity dispersion of the galaxy's bulge, the M-sigma relation, discovered in 2000. Galaxies with larger bulges have more massive central black holes. Even though the black hole's sphere of gravitational influence is far smaller than the galaxy, the black hole at the center of the Milky Way has a mass of 4 million solar masses, which is tiny compared to the Milky Way's total stellar mass of about 60 billion solar masses. Yet the two are tightly correlated across all galaxies studied. This suggests that the formation of the black hole and the galaxy are physically coupled. When the black hole accretes rapidly and launches powerful jets and outflows, those outflows can heat and disperse the gas throughout the galaxy, quenching star formation and eventually shutting down the black hole's own accretion. This process, called AGN feedback, active galactic nucleus feedback, is thought to be the primary mechanism that stops massive galaxies from forming stars indefinitely, explains why large elliptical galaxies have old stellar populations, and regulates the overall star formation history of the universe. O287 is a blazar, a type of active galactic nucleus in which the relativistic jet is pointed nearly directly at Earth, making it one of the most luminous objects in the sky at radio and optical wavelengths. At its center is a binary supermassive black hole system, a primary black hole of about 18 billion solar masses, and a secondary of about 150 million solar masses, and an orbital period of about 12 years. The secondary black hole passes through the accretion disk of the primary twice per orbit, producing optical outbursts that have been observed and recorded since the 1880s. Modeling these outbursts requires general relativistic effects, including the precession of the binary's orbit due to gravitational wave emission, and OJ287 has been used to test general relativity in the strong field regime, providing the most precise test of gravitational wave emission in a binary black hole system involving supermassive black holes. Einstein-Rosen bridges, more commonly known as wormholes, are mathematical solutions of general relativity describing a tunnel connecting two separate regions of spacetime, either two distant parts of our universe or two different universes entirely. The simplest wormhole solution, derived by Einstein and Rosen in 1935, is the Schwarzschild wormhole, the full extension of the Schwarzschild metric through both the event horizon and its time reverse, contains not one but two separate exterior regions connected by a throat through the interior. This structure, revealed in the Kruskal-Szekeres, coordinates that provide the maximum analytic extension of the Schwarzschild metric, shows that a non-rotating black hole is, in principle, connected to another universe or another region of our own universe through a geometric bridge. But the Schwarzschild wormhole is not traversable. The throat is dynamic. It expands from 0 radius to a maximum size and then contracts back to 0 in a finite time, a time shorter than any signal traveling at the speed of light could traverse the throat. Any matter or light trying to pass through the throat would be crushed by the collapsing geometry. The wormhole opens and closes too quickly to be used as a passage. For a wormhole to be traversable, it would require exotic matter, material with negative energy density relative to an observer moving through it, to hold the throat open against its tendency to collapse. Whether exotic matter in sufficient quantities can exist is not known. Quantum field theory allows small amounts of negative energy density in specific configurations, such as the Casimir effect between parallel conducting plates, but whether sufficient negative energy can be assembled to stabilize a macroscopic wormhole is far from established. Traversable wormholes remain speculative. The Penrose-Hawking singularity theorems, proved by Roger Penrose in 1965 and extended by Hawking in the late 1960s, established that singularities are not a peculiarity of perfectly spherical, perfectly symmetric solutions like the Schwarzschild metric, but are a generic prediction of general relativity whenever certain energy conditions are satisfied and a trapped surface forms. Penrose's theorem states that if a trapped surface exists, meaning a surface from which all outgoing light rays are converging, then the spacetime must contain a singularity. Since the formation of an event horizon necessarily produces a trapped surface, general relativity predicts singularities inside every black hole, regardless of the symmetry of the collapse. The theorems do not specify the nature of the singularity, only that the spacetime is geodesically incomplete, some paths through spacetime, some histories of freely falling observers, reach an endpoint in finite proper time beyond which they cannot be extended. Penrose received the 2020 Nobel Prize in Physics, shared with Andrea Ghez and Reinhard Genzel for this work. The iron K alpha spectral line, produced by fluorescence of iron atoms irradiated by X-rays near the inner edge of an accretion disk, provides one of the most powerful observational tools for measuring the spin of black holes. The line is emitted at a characteristic energy of 6.4 kiloelectron volts in the rest frame of the emitting iron. When observed from Earth, the line is broadened and skewed by the combination of Doppler shifts from the rapidly orbiting disk material and gravitational redshift from the deep gravitational potential well near the black hole's inner edge. The shape of the skewed line depends sensitively on how close the inner edge of the disk comes to the black hole, which depends on the spin. A maximally spinning black hole allows stable circular orbits much closer to the center than a non-spinning black hole. By modeling the shape of the iron line in X-ray spectra of black hole X-ray binaries and active galactic nuclei, astronomers can measure the dimensionless spin parameter of the black hole, ranging from 0 for a non-rotating black hole to 1 for a maximally rotating black hole. Several black holes have been measured to have spin parameters above 0.9, indicating near maximal rotation. The innermost stable circular orbit, the ISCO, is a concept fundamental to accretion disk physics for a non-rotating Schwarzschild black hole. The innermost stable circular orbit is located at 3 Schwarzschild radii from the center, or 6 times the gravitational radius. Inside this radius, circular orbits become unstable. A particle perturbed slightly inward will spiral into the black hole rather than returning to its orbit. The innermost stable circular orbit defines the inner edge of the accretion disk, the point inside which matter plunges rapidly into the black hole without emitting significant radiation. For a maximally rotating Kerr black hole, the innermost stable circular orbit for material orbiting in the direction of the black hole's spin is located at only half a gravitational radius from the center, much closer than for a non-rotating black hole. This proximity to the singularity means that material in the innermost stable orbit of a rapidly spinning black hole experiences a much deeper gravitational potential and therefore releases a much higher fraction of its rest mass energy as radiation. The maximum radiative efficiency of accretion is about 7% of the rest mass energy for a non-rotating black hole and about 42% for a maximally rotating black hole. For comparison, nuclear fusion, the most efficient energy source in ordinary astrophysics, converts less than 1% of the rest mass of hydrogen into energy. Accretion onto a spinning black hole is the most efficient steady energy release process in the known universe. Cygnus X1 was the first strong candidate for a stellar mass black hole identified in 1971. It is a high-mass X-ray binary, a system in which a black hole is accreting material from the stellar wind of a companion star, a blue supergiant called HD 226868. The X-ray emission from the accretion disk, with a luminosity of about 10 to the power of 31 watts, was discovered by the Uhuru X-ray satellite. The mass of the compact object was determined from the orbital dynamics of the binary and found to exceed the maximum mass of a neutron star, establishing it as a black hole with high confidence. Cygnus X1 has a mass of about 21 solar masses and is located about 6,100 light-years from Earth. The discovery prompted the physicist John Wheeler, who coined the term black hole in 1967, to bet Stephen Hawking that Cygnus X1 was indeed a black hole. Hawking characteristically bet against it, as insurance in case his own theoretical work on black holes was wrong. He conceded the bet in 1990. The Milky Way's central parsec, the region within about 3 light-years of Sagittarius A star, contains an extraordinary concentration of massive stars, stellar remnants, and hot gas. In 2018, a study using Chandra X-ray Observatory data identified a concentration of about a dozen X-ray binaries with black hole companions within 3 light-years of the galactic center, far more than expected from random distributions. The study estimated that up to 10,000 stellar mass black holes may be concentrated in the central parsec, drawn there by dynamical friction as massive stellar remnants lose energy to the surrounding stellar population and sink toward the center. The galactic center may be the densest region of black holes anywhere in the galaxy, a crowded neighborhood of invisible compact objects swarming around the supermassive black hole that dominates their gravitational environment. The Event Horizon Telescope image of M87 star, released on April 10, 2019, was the result of observations conducted in April 2017 using 8 radio observatories on 4 continents and in 2 polar regions, including facilities in Hawaii, Chile, Spain, the South Pole, Arizona, and Mexico. The combined data, amounting to about 5 petabytes, was physically shipped on hard drives to correlation centers at MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy in Bonn because the volume was too large to transmit over the internet. The correlation process required months of computation and multiple independent imaging pipelines to ensure the result was not an artifact of the data reduction. The final image, showing a bright ring of emission with a diameter of about 42 micro-arc seconds and a dark central shadow, was consistent with the theoretical prediction of general relativity for a black hole of 6. 5 billion solar masses to within the uncertainties of the mass measurement. Tonight, a black hole 1,000 light years from Earth is sitting in the dark, as it has been for millions of years, curving space-time around itself in silence. It is not threatening anything. It is not moving toward us. It is simply there, bounded by an event horizon that looks unremarkable from outside and leads to a singularity from inside. The gravitational waves from black hole mergers are passing through you right now, compressing and stretching the space around you by distances far too small to measure without a 4-kilometer laser interferometer. The information paradox is unresolved. The singularity at the center of every black hole is, in the deepest sense, unknown, a place where our most tested theories of physics cease to apply, where the fabric of space-time itself may dissolve into something our mathematics cannot yet describe. In the far future, when the last stars have faded and the universe has entered the era of darkness, the only sources of light will be the slowly evaporating black holes, each one radiating Hawking radiation at a temperature that grows infinitesimally as the black hole's mass decreases. They will persist for times of 10 to the power of 67 years and 10 to the power of 100 years. The universe as we know it will be unrecognizably transformed, but the black holes will still be there, still keeping their secrets, still bounded by their event horizons, still curving space-time in the cold and empty dark. You are lying in the dark. You are safe. The nearest black hole is 1,000 light years away. Sagittarius A star is 26,000 light years away and sitting in peaceful quiet at the galactic center. The universe has arranged things so that you exist at a safe distance from all of its most extreme objects on a small rocky planet orbiting a quiet middle-aged star in a quiet region of a quiet spiral galaxy. The black holes are keeping their secrets. They have been doing so for billions of years. They will be doing so tomorrow. You do not need to understand the information paradox before you sleep. The universe has been keeping these secrets for 13.8 billion years. It can keep them until morning. The gravitational waves from black hole mergers are passing through you right now, compressing and stretching the space around you by distances far too small to measure without a 4-kilometer laser interferometer. The information paradox is unresolved. The singularity at the center of every black hole is, in the deepest sense, unknown, a place where our most tested theories of physics cease to apply, where the fabric of space-time itself may dissolve into something our mathematics cannot yet describe. In the far future, when the last stars have faded and the universe has entered the era of darkness, the only sources of light will be the slowly evaporating black holes, each one radiating Hawking radiation at a temperature that grows infinitesimally as the black hole's mass decreases, glowing colder than any other object in the universe except the nearly empty void itself. They will persist, these black remnants of the universe's most violent births, for times of 10 to the power of 67 years and 10 to the power of 100 years. The universe as we know it will be unrecognizably transformed, but the black holes will still be there, still keeping their secrets, still bounded by their event horizons, still curving space-time in the cold and empty dark. You are lying in the dark. You are safe. The nearest black hole is 1,000 light years away. The event horizon of Sagittarius A star is 26,000 light-years away, and at the scale of the galaxy, Sagittarius A star is one of the quietest and least active supermassive black holes known, occasionally producing small flares, but otherwise sitting in peaceful darkness at the galactic center. The universe has arranged things so that you exist at a safe distance from all of its most extreme objects on a small rocky planet orbiting a quiet middle-aged star in a quiet region of a quiet spiral galaxy. The black holes are keeping their secrets. They have been doing so for billions of years. They will be doing so tomorrow. The Milky Way's 100 million black holes will be sitting in the dark tonight, every one of them invisible, every one of them patient, every one of them curving space-time in silence around the remnants of stars that died millions of years before a single human eye looked up. You do not need to understand the information paradox before you sleep. The universe has been keeping these secrets for 8 billion years. It kept them while the first cells divided in the warm, shallow oceans of early Earth. It kept them while the dinosaurs slept under ancient stars. It kept them while the first telescope was pointed at the sky. It will keep them tonight, quietly, while you breathe, and the event horizons will hold, and the singularities will remain unreachable, and the dark will be very dark indeed. Good night, and rest well. The event horizon holds.